Welcome to my Feynman. Today we're gonna do the integral of ln of x squared plus 1 over x squared plus 1 going from 0 to infinity. And today I'm going to do this in the Feynman technique way. Sorry, I mispronounced Feynman. I've mispronounced Feynman technique as Feynman technique. Sorry Feynman, I mispronounced your name. So please forgive me. I'm sorry. So Feynman technique. You can also use let x is equal to tangent theta, and then you pretty much just get secant square theta in ln of secant square theta going from 0 to infinity. And then you can put the 2 and then keep going. So today I'm going to do this in a Feynman technique way. So first thing we're gonna do, the Feynman technique says we let I of something is equal to the integral, say the same, ln of something, and then x squared plus 1. We actually have two methods to do it. One, we can put a before the x squared, and the second, we can put x squared plus a like that. But this time, I'm going to do this in this way, x squared plus a like that. Here's the, you can also put the a here, ax squared plus 1. You can also do this integral by this way. So we're gonna differentiate both sides with respect to a. You will pretty much just get first 1 over x squared plus 1. You leave it as a constant because it's a constant in the a row, and then you're gonna multiply by the derivative of this. ln of something, do the derivative, you get this x squared plus a, and then do the derivative of inside. And then since we are differentiate in the a row and the x squared is a constant, so you get 0, and then differentiate a, you get 1. So over like that, you pretty much just get this 1 over x squared plus 1 times 1 over x squared plus a. Here's the deal. Do we know how to integrate it? 1 over x squared plus 1. Yes. Do we know how to integrate this? 1 over x squared plus a. But we're gonna use a partial fraction here because whenever you multiply, it's really hard to do. I'm going to split to two different fractions. So I would like to split to two different fractions, x squared plus 1 dx, and then another. I'm not sure what is the side here. What is the side here? Because we may get some constant here. So I will leave a space to here, and then so going from 0 to infinity, and then x squared plus a like that. So I'm going to use a partial fraction here. This integral is really hard. If you use the Feynman technique, put the a here. So it will take a lot of time. So just really hard this method is. So you pretty much just get 1 over x squared plus 1 times x squared plus a. Use the partial fraction. First you get x squared plus 1 plus something. I'm going to get something on the top. Just 1 less of the power of this x squared, just ax plus b. This you get cx plus d as well. Just 1 less the power. If this is x cubed, you just get cx cubed and then dx, cx cubed plus dx squared, and then so many. There's so many things you're gonna put plus a. And then multiply by this on one side, you will get 1 is equal to like ax plus b multiplied by x squared plus a plus cx plus d multiplied by x squared plus 1 like that. And then you're gonna distribute it, you will get a times x cubed, and then plus a times small letter a x plus bx squared plus, I'm going to write the a in front, and then plus, this is just parentheses, cx cubed plus cx plus dx squared plus d. Really long. I'm going to combine it. Just combine the x cubed term first. You get a cubed, a times x cubed, and then c times x cubed. So you're gonna factor it as a plus c times x cubed plus b and then plus d times x cubed, and then do it really fast. Let me just write down an a in front. This a, we're gonna put some number. A is just a number, right? We're gonna put some number. So why a in front? I would like to a times ax. Do I forget the a here? I think so. Sorry, I forgot a, but never mind. So overall, I will get a times small letter a times big letter a, and then plus c multiplied by x, and then the constant is just ab plus d. So overall, you are going to do a system equation. So this is just compared to both sides. You get a plus c is equal to 0, like that. B plus D is also gonna be 0, and the small letter a times big letter a plus c is equal to 0, and a b plus d is equal to 1, the constant part. So here's the deal: we want a plus c is equal to 0. Small letter times a times big letter a plus c need to be 0. So you pretty much just get a is equal to 0 and then c is equal to 0 really quick. So it's really easy, right? So here's the deal: I would like to use this equation, subtract this equation, and then factor the b. You will get a minus 1 times b, and then d and d they are gone, and then 1 minus 0 is 1, divided by a minus 1 and 1. Both hands side you will get b is equal to 1 over a minus 1. So put it back on the second equation, you will get d is equal to negative 1 over a minus 1, like that. So here we know that a and c, they are both equal to 0. So let me just put down the d here. B and d. We know b is equal to 1 over a minus 1 and d is equal to that. Because they are constant in the x world, so we can just, let me just put down my 1 here. And then put down 1 over a minus 1 here. And then here I'm going to put negative 1 over a minus 1 here. I think we don't have enough space, so let me just erase it. It is really annoying. This integral is really hard, I know. Because we use the Feynman technique in this way, put an a here. But I don't think if we put an a here, it will be easy to do either. So Feynman technique is that hard. So here's the deal: we know how to do integral of this. It's the inverse tangent of x. And how to do this integral? You can write this a as what? Square root of a. And then square that. You pretty much just get, right? The first, you get 1 over a minus 1 times inverse tangent of x, going from 0, u out of a from 0 to infinity, and then this one, you get negative 1 over a minus 1. First, you get 1 over a, right? 1 over inside, 1 over square root of a times inverse tangent of x over square root of a. That's our formula of that. So, since I don't have enough a, can you guys see that? Yes, I think. So, we're gonna plug inside. Plug infinity inside, you pretty much just get pi over 2. So let me just write down as pi over 2 times a minus 1, and then 0, just subtract 0. It's nothing else. So let me continue, and then here you pretty much just get pi over 2, just pretty much just the same. Pi over 2 times our root a multiplied by our a minus 1. So that's it, and then minus 0 is just 0. So we know that I prime of a is equal to a. And then we're gonna integrate both sides. We know how to integrate this one, right? It's really easy. Integrate both sides, get I of a, integrate it, put the pi over 2 in front, and then integrate 1 over a minus 1 in the a row. You pretty much just get ln, right? ln of a minus 1. And here's the deal. Because a is a is here, make sure a should be greater or equal to 0. Even 0 here, put a 0. If a is 0, it's also gonna converge. Don't worry. So if you put if you let I of a is equal to L1 of x squared plus 1 and then over x squared plus a, make sure a need to be greater than 0 because L1 of x squared plus 1 over x squared going from 0 to infinity is divergence. So if you let the I of a, put a here, you need to assume that a is greater than 0. So this time because a is here, we can, because this I don't think if this negative it will be converges. So that's it. So let me just continue. And then because negative pi over 2 is a constant, put it inside. Just put it outside the integral. So how to integrate? Let me just do it here. How to integrate 1 over square root of a times a minus 1. This is a really weird integral, I think. But don't worry, this integral is not that bad at all. We can actually integrate. It seems that it's impossible, but we like to let a complicated function to let it be u, right? Square root of a is more complicated than this, so let u is equal to square root of a, and then I'm going to get the original. So u squared is equal to a. Differentiate both sides, you get 2u du is equal to dA. So you can get 2 times u over square root of a is u times, and then our a is just u squared minus 1 du, like that. So you will see u and u, they cancel each other out, and then how to integrate 1 over u squared minus 1. And here I'm not going to use hyperbolic function here because the original integral is going from 0 to infinity, and just I'm going to use the ln here. So let me just use, you can write this as u minus 1 times u plus 1, use the partial fraction, but this time we can do it really quick. Just use the carve-out method. So how we let u minus 1 is equal to 0? So u need to be 1. So put it in here, and then you get 2, and then 1 divided by that. You will get 1/2 here. And look at this, u minus 1, how can we let it to be equal to 0? So u need to be -1. Put it here, you get negative, and then divided by it. You get -1 over 2. You pretty much just cancel the 2 and then integrate 1 over u minus 1. You will get ln of u minus 1. Just another epsilon, because we assume that we let u is equal to square root of a. A need to be greater or equal to 0. So never mind, just another domain here. And then subtract 2 and 2, they are cancelled. You pretty much just get ln of u plus 1. And then you can just combine the lower form, but this is the minus. ln something minus something. You pretty much just get ln of this. And then our u is just square root of a. Let me write it as square root of a minus 1 divided by square root of a plus 1, like that. And that's our integral of this. Don't forget to add a plus c after finishing the integral. So overall, let me just write down, this is equal to ln of square root of a plus 1. We finish it. This is just ln of square root of a minus 1 over square root of a plus 1. It seems like it's really crazy, but let me just continue. Because we haven't finished yet, we can simplify more. So here's the deal. We have a negative side here. We can bring it inside the lower sum, and then we can flip it. So we can do a reciprocal of that, right? ln of a minus 1, and then plus pi over 2 multiplied by ln of square root of a plus 1, because you flip it, and the square root of a minus 1. Here, I'm going to multiply by the conjugate of this, square root of a minus 1. multiply by square root of a plus 1, multiply by square root of a plus 1. So you will get pi over 2 times ln of a minus 1 plus pi over 2 times ln of. Here you will get, on the top you will get square root of a plus 1 and then square that. So on the denominator you get square root of a minus 1 times that, you pretty much just this square minus this, you pretty much just get a minus 1 here. So here's the deal. ln of quotation, we can use the quotation, just use the, what's that called? The division rules of the logarithm. So here, pi over 2 times ln of a minus 1, and then distribute the pi over 2, and then this square root of a plus 1 square, and then you're gonna get minus here, minus pi over 2 times ln of a minus 1. Check this out. This is positive and this is negative. This and this, they cancel each other out. Pi over 2 times ln of a minus 1, they cancel each other out. So you can also just put down a 2 here, because it's always gonna be a positive number inside. So put down a 2 to here. So you simplify to pi times ln of square root of a plus 1, like that. But however, after you integrate, you need to add a constant here, because we are not sure what is the constant here. So let me just continue. So we already finished it. Just let me just erase this. I think you already just know what is the step, right? So original, we get what is our I of a, right? This pi over 2, pi times ln of square root of a plus 1. Let me just erase this. This integral is really hard. So we know that this is equal to our pi times ln of square root of a plus 1 plus c. And I'm going to choose a is equal to 0 here. Right? A is equal to 0 because I already say it is converges. It converges. So we choose a is equal to 0. You pretty much just get, you can put down a 2 outside the integral, you get 2 times ln x over x squared plus 1 dx. And right hand side you will get, put a 0 into it, you get pi times ln 1 plus c. So overall you will get, let me put down a c in front, and let me do the integral of this. And this is a really famous integral. You can let x is equal to tangent theta, and then this and that secant square theta just cancel each other out. You pretty much just integrate ln of tangent theta from 0 to pi over 2, and that solution is just equal to 0. But I'm going to show you how to do that. So we can not only just let x is equal to tangent theta, we can also do that. But this time we're gonna let I is equal to that. I is equal to this question. And then we're gonna let x is equal to 1 over t. Just a variable t. And then our dx is just equal to negative 1 over t squared. Just put it here. We have negative, and then put 0 into it. 1 over 0 is infinity, and then 1 over infinity is just 0. And then you pretty much just get ln of 1 over t, and then over our x is just, but because x is equal to 1 over t, and then t is equal to 1 over x, if we want to get to our x row, get into our t row, just because x is equal to 1 over t, pretty much t is equal to 1 over x, just put 0, just pretty much just stamp, just put it inside. So here x is equal to 1 over t squared plus 1 multiplied by, we already put down a negative outside, so we forget our dt, and then multiply by 1 over t squared dt. So overall, you can flip it. Going the integral going from infinity to 0, you can flip it fast to the negative side. You can get going from 0 to infinity, and then the denominator you pretty much just multiply by t squared inside. First you multiply by t squared, and then t squared and t squared are cancelled. You pretty much just get this t squared plus 1, and then on the top you can write this as ln of t power of negative 1. You can put the power outside, you can get this, right? T over t squared plus 1 dt. Since t is a dummy variable, you can name it whatever you want. Just name it as x ln x over x squared plus 1 dx. Then you just need to add these two integrals together. You get this integral is just equal to 0. So you pretty much just get a constant. 2 times 0 is just 0. So pretty much this original question, we already know that I of a is equal to pi times ln of square root of a plus 1, like that. But this equal to what? Just put a 1 into this. So this original question is equal to I of 1. Just put down 1 inside, you will get pi. Let me just show you some step here. Pi times ln of square root of 1 plus 1 is pretty much just pi times ln 2, like that. Yes, it's really good, right? So that's it. The integral of ln of x squared plus 1 over x squared plus 1 over going from 0 to infinity is just pi times ln. Just pi times ln 2, yes. Of course, you can do integral of put a 2, 3, you can get a lot of answers here. And you can also just put down a 0 here, just that, right? Just put down a 0, you pretty much just get 0 here. And it's really, really cool, right? Yes, that's our answers. Feynman technique.